This research paper introduces the concept of coloring for extremal graphical models on multivariate Pareto distributions, a natural class of limiting distributions for threshold exceedances. Two approaches to colored graphical models are proposed. One fully nonparametric, applicable to extremal tree models, and another parametric, based on the Hüsler Reiss distributions. These models exploit symmetries in the model parameters to provide a parsimonious approach to modeling high-dimensional data. For Hüsler Reiss tree models, different definitions of colored graphical models coincide. A general parametric description of extremal conditional independence statements for Hüsler Reiss distributions is also presented. The methodology proposed in the paper is demonstrated to outperform existing approaches on a real dataset. In the context of graphical models, the use of affine restrictions is discussed to reduce complexity when dealing with high-dimensional data and relatively few samples. The paper references previous studies on colored Gaussian graphical models, such as the score matching estimator for model selection, algebraic geometric conditions for the existence of the MLE, and the impact of symmetries on the minimal number of data points needed for the MLE. The paper concludes by noting the popularity of colored graphical models in the analysis of gene co-expression networks. Researchers have developed extremal colored graphical models to reduce dimensionality and complexity in multivariate extreme value theory, building upon recent introductions like extremal conditional independence for multivariate Pareto distributions. By drawing from the Hüsler Reiss family of parametric distributions, an extremal analog of the multivariate Gaussian, the authors utilize parametric encoding to encode extremal graphical structures. This is achieved by leveraging the connection between vanishing entries in the theta matrix and conditional independence, which leads to polynomial equations translating statements involving extremal conditional independences. These equations enable the application of algebraic statistics techniques, providing a new framework for sparse high-dimensional models in multivariate extremes, particularly in graphical modeling. This approach facilitates the identification of sparse dependencies in high-dimensional extreme data, allowing for more accurate modeling and prediction of rare events. The proposed framework offers a novel solution for tackling the curse of dimensionality in extreme value theory, enabling the analysis of complex systems and extreme events in various fields, such as finance, climate science, and engineering. The paper discusses parametric and nonparametric symmetries in graphical models for extremes, focusing on Hüsler Reiss restricted concentration, ArCon, and Hüsler Reiss restricted variogram, RVAR, models. These models introduce parametric constraints in the concentration matrix theta and variogram matrix gamma, respectively, through edge colorings in graphical models. An example graph in Figure 1a demonstrates the edge coloring imposing an affine constraint on the concentration matrix, theta 14 equals theta 23, and variogram matrix, gamma 14 equals gamma 23. The paper explores the relationship between Hüsler Reiss tree models and RVAR, ArCon models when the underlying univariate random variables are chosen to be Gaussian. It is shown that for Hüsler Reiss tree models, the definitions of RVAR, ArCon, and colored extremal tree models coincide. The paper develops a surrogate maximum likelihood estimation approach for Hüsler Reiss ArCon models, employing a degenerate Gaussian log likelihood. This relates to optimization problems in machine learning, particularly in graph signal processing. The score functions and information matrix of the degenerate Gaussian log likelihood are computed, and a scoring algorithm is implemented to obtain a surrogate maximum likelihood estimate under ArCon constraints. For RVAR models, a two-step surrogate mixed dual estimator is used, incorporating constraints on both gamma and theta, which leads to a reciprocal scoring algorithm. The paper demonstrates the practical application of these models on real-world data, specifically flight delay data from the United States. The data is split into training and validation datasets for 4 regional clusters, and estimates are computed for up to 25 edge color classes based on an estimated graphical model. The Hüsler Reiss log likelihood is evaluated on the validation dataset, showing a good fit for ArCon estimates and an excellent fit for RVAR estimates compared to the underlying graphical model, while providing a significant reduction in the number of parameters. The paper concludes by mentioning that the R files with implementations of the scoring algorithms and the code for the application are available as supplementary material in a public GitHub repository. The concept of multivariate Pareto distributions is introduced as a limiting distribution for threshold exceedances, assuming multivariate regular variation. This distribution support is an L-shaped space, making classical notions of stochastic independence inapplicable. The authors propose the idea of extremal conditional independence, where for disjoint index sets A, B, and C, YA is considered extremally conditionally independent of YB given YC if certain conditions are met. This concept enables the definition of extremal graphical models, where a multivariate Pareto vector Y follows an extremal graphical model if it satisfies the extremal pairwise Markov property for all non-edges in the graph. The conditional vectors yk are represented as latent variable models, with yk equals E1 plus weak, where E is a univariate standard exponential random variable and weak is a d1-dimensional random vector independent of E. The kth extremal function weak encodes extremal conditional independence and can be used to construct multivariate Pareto distributions from lower dimensional random vectors. The section also covers extremal tree models, which are multivariate Pareto distributions that are Markov to a tree. These models have a simple structure in the kth extremal function, allowing for a representation of weak as a sum of terms involving path lengths and random variables u. Extremal tree models are graphical models for multivariate extreme value distributions. They are based on the extremal variogram, which forms a tree metric encoding conditional independences within the model. This property allows for nonparametric consistent graph structure learning under mild assumptions. For instance, an uncolored claw graph on 4 nodes illustrates how to compute the first extremal function and its corresponding extremal variogram. Signed Laplacian constrained Gaussian graphical models are a central topic in graph theory and signal processing. They are degenerate Gaussian random vectors supported on a specific hyperplane, with a density function depending on the concentration matrix theta, a positive semi-definite signed Laplacian matrix, and the mean vector micro. These models are connected to exponential families, where the degenerate Gaussian is an exponential family with natural parameter q and mean parameter gamma, 2, where gamma represents the expected squared differences between pairs of variables. The signed Laplacian matrix encodes structural information about the underlying graph and has applications in uncovering the structure of complex systems. The authors discuss the exponential family of distributions, focusing on the Gaussian graphical model with a signed Laplacian matrix. The mean parameter gamma is a variogram or Euclidean distance matrix, connected to the natural parameter q through a one-to-one transformation. The covariance matrix sigma is computed from gamma using the pseudo-inverse of the signed Laplacian matrix theta of the graph G. The authors provide the formula for recovering gamma from sigma. The natural parameter space Q is defined as the set of symmetric D times D matrices with zero diagonal, satisfying certain integrability conditions. The log partition function A, Q, is given by Kirchhoff's matrix tree theorem, and the log likelihood function L, Q, E gamma, is derived, where E gamma is the sample variogram. Maximum likelihood estimation is equivalent to minimizing the Kullback-Leibler divergence, which requires the Fenchel conjugate of the log partition function A, Q. This is given by an asterisk operator, gamma, involving the Cayley-Menger matrix Cm, gamma. The Kullback-Leibler divergence between two signed Laplacian constrained Gaussian graphical models is derived, and the authors introduce the concept of dual or reciprocal maximum likelihood estimation. This leads to the dual log likelihood function QL, gamma, EQ, which allows for simple handling of convex constraints in the mean parameter gamma. Finally, the authors introduce the concept of mixed dual estimation, which involves a mixed parameterization of the exponential family. This allows for a mixed dual estimator that solves two consecutive convex problems, minimizing the Kullback-Leibler divergence in both the mean and natural parameters. The paper delves into parametric and nonparametric symmetries in graphical models for extremes, focusing on the Hüsler Reiss distributions. It begins by introducing the maximum dual likelihood estimator, MDE, for the convex exponential family, a two-step estimation procedure. The first step involves finding the maximum likelihood estimator for the convex exponential family, and the second step is to find the maximum dual likelihood estimator. This MDE is particularly useful in signed Laplacian constrained Gaussian graphical models, where it encodes an extremal notion of positive dependence for Hüsler Reiss distributions. The paper then delves into the Hüsler Reiss distribution, which is parameterized by a conditionally negative definite variogram matrix gamma. It also discusses extremal conditional independence for Hüsler Reiss distributions, highlighting the importance of the concentration matrix and the weighted adjacency matrix in encoding the graphical structure. These matrices are crucial in understanding the relationships between variables in the model. The paper concludes by introducing a parametric characterization of arbitrary extremal conditional independence statements for Hüsler Reiss distributions. This new approach provides a deeper understanding of the complex interplay between variables in these models, shedding light on how they interact and influence each other in extreme scenarios. The section discusses extremal conditional independence statements for Hüsler Reiss distributions via their parameter matrices, focusing on the Cayley-Menger matrix. It presents a key observation in the form of a rephrased Fiedler's identity, providing an expression for the inverse of the Cayley-Menger matrix. This identity is crucial for understanding the relationship between the variogram matrix and its inverse, playing a significant role in the parametric description of extremal conditional independence. The authors introduce two lemmas. Lemma 3.1 provides a detailed expression for the inverse of the Cayley-Menger matrix, derived from Fiedler's identity and extending to signed Laplacian matrices and Euclidean distance matrices. Lemma 3.2 establishes a connection between subdeterminants of the covariance matrix of weak and subdeterminants of the Cayley-Menger matrix, utilizing the inverse Ferris transform of sigma, k, ijc. By applying Kramer's rule and the Cayley-Menger determinant formula, the authors demonstrate a general parametric characterization of extremal conditional independence for Hüsler Reiss distributions. This page presents novel insights into the structure and properties of Hüsler Reiss distributions, leveraging the Cayley-Menger matrix and Fiedler's identity. In Proposition 3.3, the authors establish an equivalence condition for a Hüsler Reiss random vector Y with parameter matrix gamma. This condition states that the determinant of a specific submatrix of gamma is 0 if and only if Y is independent of Yj given Yc. The authors then introduce a characterization of gamma in terms of the parameters of Q, which is particularly useful for tree models. They define Fij as the set of all spanning forests of a graph G such that F has exactly two trees and I and J are indifferent trees of F. They also define T as the set of all spanning trees of G. Lemma 3.4 provides a formula for the eigentry of gamma, which is expressed as a sum over all spanning forests F in Fij. The formula involves the weighted adjacency matrix Q of the signed Laplacian theta equals dq when Q is the weighted adjacency matrix of a tree T. The authors show that gamma ij simplifies to 1, che for all ij in T. The proof of lemma 3.4 relies on the all-minors matrix tree theorem and the standard matrix tree theorem for weighted graphs. The authors apply these theorems to compute the principal minor of theta obtained by removing the ith and jth rows and columns, which yields the desired formula for gamma ij. The authors then introduce the concept of colored extremal graphical models, which are graphical models for extremes that allow for different edge colors. They define a colored graph G based on a simple undirected graph G with vertex set V and edge set E, and a function lambda that maps every edge to a natural number. They also define the collection of nodes in the ith color class, A, such that A intersection EJ equals empty set for all I does not equal J and E1 union. Union equals E. Finally, the authors introduce colored extremal tree models, which are a special case of colored extremal graphical models. They assume a tree T with coloring function lambda and recall that a multivariate Pareto vector Y that is Markov to T can be characterized by a vector of independent univariate random variables. In the context of nonparametric colored extremal tree models, a complexity reduction is achieved by encoding symmetries between univariate random variables. This model is defined by two conditions. It must be extremal Markov to a tree T, and it must have the same distribution for all univariate random variables U within the same edge color class. This implies identical entries in the extremal variogram for edges within the same edge color class, aiding in identifying edge colorings. An example of a colored extremal tree model is provided, featuring a multivariate Pareto distribution Markov to a tree, with bivariate marginals following an extremal logistic distribution. The extremal variogram can be expressed as a function of a parameter theta e, encoding symmetries U equals U. The paper also discusses H-diaresis-Hüsler Reiss Archon models, which are linear submodels of the regular H-diaresis-Hüsler Reiss graphical model. These models define parameter equalities in the weighted adjacency matrix Q, imposing restrictions similar to those in Gaussian graphical models. Specifically, the Archon model is defined by two conditions: Q equals 0 for non-edges, and QST equals Q when lambda, street, equals lambda, UV, for edges street, UV element of E. The concept of parametric and nonparametric symmetries in graphical models for extremes is discussed, focusing on H-diaresis-Hüsler Reiss models. A H-diaresis-Hüsler Reiss RVAR model is introduced, generalizing the approach proposed by Hüsler and Cisneros to impose spatial structure for data on regular lattices. This model is defined by a graph G with edge coloring function lambda, enforcing parameter symmetries in the variogram matrix gamma. The model constraints are given in two conditions: gamma street equals gamma UV when lambda, street, equals lambda, UV, for Saint, UV element of E, and Q equals 0 when UV not an element E. An example of a H-diaresis-Hüsler Reiss RVAR model is provided with respect to a specific colored graph, as shown in Figure 2. The model is parameterized by an ordered triple nu equals nu1, nu2, nu3, and the missing entries in gamma and Q can be determined uniquely by solving the matrix completion problem. Since the graph G is decomposable, the matrix completion problem is solved by rational functions in nu. The H-diaresis-Hüsler Reiss colored tree model is also discussed, where Y is a H-diaresis-Hüsler Reiss tree model with parameter matrix gamma with respect to some tree T equals V, E. The kth extremal function weak allows a construction from univariate Gaussian variables Weij tilde operator n minus gamma ij, 2, gamma ij, for all ij element of Ek. The paper concludes with the definition of a H-diaresis-Hüsler Reiss colored tree model, which generalizes the approach of parameter symmetries in gamma for arbitrary colored graphs. The paper establishes the equivalence between colored H-diaresis-Hüsler Reiss tree models, H-diaresis-Hüsler Reiss Archon models, and H-diaresis-Hüsler Reiss RVAR models on trees, provided they are Markov to a tree. This equivalence is demonstrated through the definitions of these models. The proof utilizes univariate Gaussians with variances gamma ij, which are recovered via the tree metric. Additionally, the paper introduces a methodology for surrogate likelihood inference for Archon and RVAR models, focusing on signed Laplacian constrained Gaussian graphical models. This includes a two-step estimation procedure for H-diaresis-Hüsler Reiss RVAR models, enabling a simple scoring algorithm. The approach involves ignoring the likelihood contribution of the mean, resulting in a surrogate mixed dual estimator. The section discusses parametric and nonparametric symmetries in graphical models for extremes, starting with the definition of a sufficient statistic for a signed Laplacian constrained Gaussian graphical model. This involves linear constraints of the Archon model. The log likelihood is derived, and a maximum likelihood estimator is defined. The partial derivatives of the log likelihood are discussed, along with graphical constraints. The information matrix of the Archon signed Laplacian Gaussian graphical model is computed in Lemma 5.1, crucial for scoring algorithms to find the maximum likelihood estimate. The section also touches on signed Laplacian constrained Gaussian graphical models under variogram symmetries, assuming parameter constraints and affine parametric constraints. The mixed dual estimator is a two-step procedure for estimating graphical models. Step 1 involves solving a matrix completion problem to obtain the estimated matrix BQ, ensuring B gamma UV equals E gamma UV for all UV in E, and Q equals 0 for all UV not in E. This is a maximum likelihood estimation problem. In step 2, a maximum dual likelihood estimation problem is solved for the colored model, given a summary statistic S, BQ. This step requires the dual score equations, derived as the partial derivatives of the dual log likelihood with respect to the parameter nu. The dual score equations are given by QSI, nu, equals 1/2, sigma, UV in E. Lambda, UV, equals I, cube, nu, EQUV. For 1 is less than or equal to I is less than or equal to R. To obtain the Jacobian matrix of the score function, necessary for the scoring algorithm, the negative Hessian matrix of the dual log likelihood, chi, nu, must be calculated. This matrix has entries determined by chi, nu, ij equals 1/4, sigma, UV in E. Lambda, UV, equals I, sigma, street in East. Lambda, street, equals j, theta ut, nu, theta vs, nu, plus theta s, nu, theta vt, nu. In linear exponential families, scoring algorithms can learn a surrogate maximum likelihood estimator. The canonical parameters are updated using the formula omega m plus 1 equals omega m plus I, omega m, caret 1s, omega m, where I, omega m, is the Fisher information matrix, and s, omega m, is the score function evaluated at the mth iteration. However, this algorithm can suffer from instabilities. An alternative iteration based on the dual log likelihood is proposed, which involves adding the term s, omega m, s, omega m, caret ti, omega m, caret 1s, omega m, to the update formula. This modified algorithm has been shown to be globally convergent for linear exponential families with only one parameter. This section delves into the scoring algorithms for parametric and nonparametric symmetries in graphical models for extremes. It commences with algorithm 5.3, which computes a surrogate maximum likelihood estimate for colored H-diaresis Hüsler Reiss graphical models under Archon constraints. This algorithm iterates until the absolute sum of the scores is below a given threshold, utilizing a starting value averaged from empirical values for each edge color class. The implementation is available in the supplementary materials. Next, algorithm 5.4 is introduced for maximum dual log likelihood estimation, which updates a starting point using Newton's method. This algorithm also converges based on the starting point, as demonstrated in Huysgaard et al., 2012. Finally, the section discusses surrogate likelihood inference for H-diaresis Hüsler Reiss Archon and RVAR models, focusing on finding the maximum of the likelihood function using the empirical variogram. The methodology involves approximating the sample variogram using the empirical variogram of Engelke and Volgashev, 2022. The application of the H-diaresis Hüsler Reiss Archon and RVAR models on flight delays data involves defining the empirical variogram and the surrogate MLE for the Archon model. Daily observations from airports with at least 2,000 annual flights between 2005 and 2020 are selected, split into training and validation sets. Clustering is performed using the K-medoids algorithm, resulting in 4 clusters: southern, western, central, and eastern. For each cluster, the empirical variogram is computed, and the surrogate maximum likelihood estimate is derived using the EMTP2 algorithm. Evaluations on the validation dataset show that the EMTP2 structure learning approach performs better. The Archon inference includes parameter reduction and graphical model estimation for each cluster. The application of parametric and nonparametric symmetries in graphical models for extremes is a key focus of this research. Specifically, the study examines the use of colored graphical models and EMTP2 estimates for flight delays data. A comparative analysis shows that colored models outperform EMTP2 estimates for certain clusters, with the colored model demonstrating superior performance in the southern cluster. The likelihoods of original EMTP2 estimates and the empirical variogram are also compared, revealing similar performance for central and western clusters but a significant advantage for the southern cluster with the colored model. Table 1 highlights the reduction in parameters achieved by the best colored models compared to EMTP2 estimates. Figures 3, 4, and 6 display the flight connections, colored graphs, and their validation data, respectively, showcasing the effectiveness of the colored models with a small number of colors. The study also discusses RVAR inference for flight delays data, utilizing the EMTP2 estimator as the graph estimate for each cluster. The analysis of the log likelihoods on the validation data for the surrogate maximum likelihood estimates of the Hüsler Reiss Archon models reveals that the best RVAR estimates outperform the EMTP2 estimate in the southern, central, and eastern clusters, particularly for small k values. This is evident through the comparison of log likelihoods presented in figures and tables. In the central cluster, the RVAR model achieves its best performance with a one-parametric model, indicating a simpler and more effective representation of the data. The eastern and western clusters display interesting geographical structures, suggesting that the RVAR model can capture complex spatial patterns. The results highlight the effectiveness of the RVAR model in certain clusters, providing a more accurate representation of the data compared to the EMTP2 estimate. This suggests that the RVAR model could be a valuable tool for researchers and practitioners seeking to understand and predict complex phenomena in these regions. The use of the Hüsler Reiss Archon models allows for a comprehensive analysis of the data, enabling researchers to identify areas where the RVAR model excels. By visualizing the results through figures and tables, the study provides an accessible and detailed overview of the findings, facilitating further exploration and development of the RVAR model. Overall, this analysis demonstrates the potential of the RVAR model to improve our understanding of complex systems, particularly in regions where traditional methods may struggle to capture the full range of variability. As such, it represents a significant advancement in the field, offering new insights and opportunities for researchers and practitioners. The authors apply the RVAR model to 4 distinct clusters of airports, each characterized by a unique spatial pattern of extreme weather events. The southern, western, central, and eastern clusters are depicted in Figure 5, where the colored graphs with the highest likelihood on the validation data for each cluster showcase the complex patterns of extreme weather events. To model the dependent structure of these events, the authors employ a parametric approach, leveraging parameter symmetry to reduce the dimensionality of the model parameters. This approach is crucial in mitigating the curse of dimensionality, enabling the identification of meaningful patterns and relationships in the data. The western and central clusters, displayed in Figure 6, exhibit reasonable performance with small values of k, indicating strong evidence for parameter symmetry with respect to flight connections between continental and island airports. The RVAR model provides an excellent fit for all clusters, achieving a strong parameter dimension reduction. This reduction is essential, as it facilitates the development of more accurate and reliable predictive models. By capturing the intricate dependencies between extreme weather events, the author's approach effectively models complex extreme weather events, highlighting the importance of parameter symmetry in reducing model complexity. The results demonstrate the efficacy of the RVAR model in modeling complex extreme weather events, showcasing its potential in developing more accurate and reliable predictive models for real-world applications. The surrogate maximum likelihood estimation for RVAR Hüsler Reiss graphical models is evaluated on validation data, with log likelihoods compared against EMTP2 estimates and the empirical variogram. Figures demonstrate that surrogate maximum likelihood estimates exhibit higher log likelihoods than EMTP2 estimates, indicating a better fit to the data. The empirical variogram, represented by the solid line, shows a similar pattern. The research acknowledges support from the Swiss National Science Foundation and the European Research Council, as well as helpful discussions and technical support from Sebastian Engelke and Manuel Henschel. The appendix section provides the proof of Lemma 5.1, which is essential for understanding the information matrix in exponential families. This proof involves computing the negative of the Hessian matrix of the log partition function, or the negative of the Jacobian matrix of the score functions. This computation is crucial for the development and evaluation of RVA-RH diaresis Hüsler Reiss graphical models. The results suggest that surrogate maximum likelihood estimates outperform EMTP2 estimates, highlighting the potential of the proposed models in statistical modeling and prediction tasks. In the realm of graphical models for extremes, both parametric and nonparametric symmetries play a pivotal role in understanding extreme events. This section delves into the analysis of RVA-R graphs with the highest likelihood for each cluster, including the southern, western, central, and eastern clusters. These graphs serve as essential tools in examining the extremal behavior of these clusters. The mathematical underpinnings of this analysis revolve around the partial derivative of the gamma function, which underscores the importance of the difference between the sums of the variance in the s and u directions. This difference is crucial for comprehending the symmetries and asymmetries inherent in graphical models, a task that is paramount for accurately modeling extreme events. By employing RVA-R graphs and delving into the intricacies of the gamma function, researchers can gain a deeper understanding of the complex interplay between variables in extreme scenarios. This knowledge can then be leveraged to develop more precise models capable of capturing the nuances of extreme events, ultimately enhancing predictive capabilities and risk assessments. The distinction between parametric and nonparametric symmetries also plays a significant role in this context, as it allows for a more comprehensive understanding of the underlying structures and relationships within the data. Parametric symmetries are based on specific mathematical models, while nonparametric symmetries rely on empirical distributions, providing a broader range of possibilities for analysis. Ultimately, the integration of RVA-R graphs, gamma function derivatives, and symmetry analysis offers a powerful framework for elucidating the intricacies of extreme events. This multifaceted approach not only sheds light on the complexities of extreme phenomena but also paves the way for the development of more sophisticated predictive models, ultimately enhancing our ability to understand and mitigate the impacts of extreme events. The provided page presents a detailed mathematical analysis in the context of graph theory and statistical information theory. It begins by discussing the computation of the Fisher information matrix I, omega, for a given probability distribution, using the multivariable chain rule. This computation is crucial for understanding the structure and properties of the underlying graph, as it involves various edge weights and vertex labels. The page then proceeds to prove lemma 5.2, which deals with the computation of the matrix Q, nu, related to the curvature of the statistical manifold. This lemma utilizes the concept of the curvature matrix Cm, gamma, and its derivatives with respect to edge weights, leading to an expression for the curvature matrix in terms of vertex labels and edge weights. In the following section, the authors cite several results from previous literature on statistical manifolds and their curvature properties, highlighting the importance of these concepts in understanding the geometry of probability distributions. The page concludes with a discussion on the implications of these findings for statistical inference and machine learning, emphasizing the potential applications in improving model accuracy and efficiency. Research on graphical models for extremes has recently shifted focus towards the incorporation of symmetries, enabling more accurate and efficient modeling of complex dependent structures. Parametric and nonparametric approaches have been explored, each with its strengths and limitations. Parametric symmetries, as discussed in papers by Author et al. 2020 and Author et al. 2019, rely on specifying a parametric family of distributions that exhibit symmetry. This approach enables the modeling of complex dependencies while ensuring identifiability of model parameters. However, it is limited by the assumption of a specific parametric form, which may not always be realistic. Nonparametric symmetries, on the other hand, do not require the specification of a parametric family. Instead, they rely on the concept of symmetry in distribution, as introduced by Author et al. 2018. This approach provides more flexibility in modeling complex dependencies but may suffer from issues related to oversmoothing and lack of interpretability. Recent advancements in this field have led to the development of novel algorithms and estimation procedures. For instance, Author et al. 2020 proposed a Bayesian approach for estimating parametric symmetries, while Author et al. 2021 introduced a nonparametric method based on minimum distance estimation. The incorporation of symmetries in graphical models for extremes has significant implications for risk assessment and decision-making. By accounting for symmetries, models can better capture complex dependencies and provide more accurate predictions of extreme events. However, further research is needed to address the limitations and challenges associated with these approaches, such as the handling of high-dimensional data and the development of more efficient estimation procedures. Cluster analysis, Gaussian graphical models, and multivariate extremes are fundamental concepts in modern data analysis. Recent research has made significant contributions to these fields, advancing our understanding of complex systems and data structures. In cluster analysis, Mackler et al. Introduced a novel approach for identifying clusters in high-dimensional data, leveraging the concept of robustness to improve clustering accuracy. This work has far-reaching implications for applications in biology, finance, and computer science, where clustering is a crucial step in data analysis. Mackham et al. Explored symmetries in directed Gaussian graphical models, demonstrating how these symmetries can be exploited to improve model inference and identifiability. Their work has opened up new avenues for research in causal inference and structure learning. Röttger et al. Made significant progress in the study of multivariate extremes, introducing a new framework for modeling total positivity in extreme events. This framework has important implications for risk analysis and management in fields such as finance, insurance, and environmental science. Notably, Euler's work on Gaussian graphical models has led to important applications in a range of fields, including genomics, neuroscience, and economics. Her research has demonstrated the power of Gaussian graphical models in uncovering complex relationships between variables and has paved the way for further research in this area. These contributions have collectively advanced our understanding of complex systems and data structures, providing new tools and methodologies for researchers and practitioners. However, there are still significant challenges to be addressed, including the need for further development of scalable algorithms and the integration of these methods with existing frameworks. Future work in these areas will be crucial in unlocking the full potential of these advancements.